Okay, we are going to start this lesson with dealing with some Maclaurin series. So, if I were showing everything to you in class, I would have shown you going through each and every one of these, creating the Taylor series. We'd look at the patterns. You'd say, "Oh, guys, I see the patterns," but we don't have that kind of time. So today, I'm just going to walk you through some of the Maclaurin series that you should have up in your head that you really should memorize. Now, should you memorize these for the AP exam? I can't really tell. So the good news is that I don't think you need to have all these memorized for this year's exam, but it's possible and they're not that hard to memorize. All right. So we're going to keep moving here. I found an external webcam. So you're going to see like part of my face as I go through these. Here are a couple Maclaurin series that you should really memorize. So remember, Maclaurin means it's centered at 0. So if we look at this first one right here, instead of memorizing this, I want you to be able to look at this and say, wait a second. If I wanted to make a series, well, I didn't mean to scribble on it. If I wanted to make a series for 1 over 1 minus x, I'm not going to memorize that. That's silly. What you should notice is that's an a over 1 minus r form, where a is 1 and r is x. And so the series is 1 times x times x times x times x, and you get a geometric series. Same with this second one. So these two yellow things are both geometric series. The first one you just multiply by x, the second you multiply by negative x. So do you need to memorize these? No. What you need to do is recognize that if something is in that a over 1 minus r form, it would have a geometric series to accompany it. E to the x. Should you memorize this one? Absolutely. If there's one that you should memorize, whether it's on the exam or not, it's e to the x. E to the x has the series 1 plus x squared over 2 plus x cubed over 3. There's factorials on the bottom, so 2 factorial, 3 factorial. And then it just keeps going. It has every term, all of them are positive, and the factorial and the exponent match. Okay. This converges for all values of x. So if you were to write out this entire series for e to the x, you would get the entire e to the x function. How do I memorize that? I remember these things with goofy little ways, and I say e means everything because this one has everything. It has all of the powers. It doesn't have just evens or odds, which you'll see in a second. Some don't. It has evens and odds. Everything is positive. Everything has a factorial. After that, we have y equals sine x. And if you look at sine x, you still see the exponents and the factorials match. But what you should notice this time is there aren't any evens, it's all odds. The sine function is an odd function. Therefore, its polynomial representation only has odd exponents and factorials. The other thing you will notice is that it alternates. You have a positive and then a negative, and then a positive and then a negative. So the sine function alternates and it has all odd exponents and odd factorials. All right. Wow, my face is huge in there. Okay. What do we have next here? We've got cosine x. Well, the cool thing about cosine x is sine and cosine are nearly identical, except that one has half of it and the other has the other half. Cosine's even, so it has all even exponents and factorials, but it also alternates. So what do you have to remember is that cosine is even and sine is odd, and you just have to think about the graphs of sine and cosine to remember which is which. Or, I told you, I have stupid ways to remember these. Okay, cosine starts with C. C looks a lot like E, E for even. And then once you know cosine is even, sine is odd. I know it's stupid. The better way would be to remember that sine is an odd function and therefore has odd exponents. The ln function, y equals ln 1 plus x. I got to be honest, I never memorized this one. It just doesn't stick in my brain anytime. So I'm going to tell you, you don't have to memorize this function. If you really wanted to, what you do is you take the derivative of ln 1 plus x, and the derivative of ln 1 plus x is 1 over 1 plus x, which is geometric. And then you take the antiderivative term by term to find the ln 1 plus x series. I just don't bother memorizing it because it doesn't come up that often. So don't worry about that one. And then last but not least, we have inverse tan. And I know how much you guys all love inverse trig functions. Inverse tan, though, not that bad. If I look at it, it's got odds, just like sine did, except it does not have factorials. Because this is not the real reason, but how do I remember which one has the factorials and which one doesn't? Sine has an I, and an I upside down looks like an exclamation point. Inverse tan, or at least this representation, does not have an I and therefore does not have an exclamation point. Stupid, but it's effective. So you just need to know, if you know inverse sine, you also know inverse tan, just take off the factorials. All right. Okay. So why do we have to memorize these? What can we do with it? Now I can make series for everything on this next page. It says using the patterns on the previous page, create series to model each of the following functions. So let me show you how I do that. All right. So if I look at this first one, I'm going to label these A, B, and C. So if I want to label these A, B, and C, A is an A over 1 minus R form. I'm going to move my webcam back here. And let's see. Did that work? That worked. A is an A over 1 minus R form. So A equals 1, R equals negative x cubed. So I have 1 times negative x cubed times negative x cubed times negative x cubed. And there's my series. Now, what did I say up here? It says use the patterns to create a series to model each of the following. Write out the first 4 non-zero terms and the general term. All right, so now I need a general term for this. Well, my general term is going to be A times R to the n minus 1. I don't know why my computer does that sometimes. So A times R to the n minus 1. Ta-da! There's my series. I can do the same thing for B. B is also geometric, except this time A is 4x and R is x. So I'd have A times x times x times x. So I have A times R to the n minus 1. Okay, easy peasy with the fractions. There you go. Now, what do we do with these other ones? So if I come down here to part C, C is negative sine 2x over 3. So what I'm going to do first is I'm going to write out the sine function. So sine is odd, so it has all the odd exponents. So I have x, and it alternates, minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. Okay. If you're wondering, wait, Ms. Member, how do I memorize the general term? I wouldn't memorize it. I would just think about it because there's lots of forms for the general term. My general term here is going to be negative 1 to the n, maybe n plus 1, n minus 1. I'll fix that in a second because it alternates. And then I have all odd exponents over odd factorials. So x is raised to an odd. I'm going to call it 2n plus 1. And then on the bottom, I also have 2n plus 1. You can have 2n plus 1. You can have 2n minus 1. Totally up to you. Then I just need to see if I pick a certain value for n, do I start the alternating in the right place? So let's see. If I pick n equals 1, this would be x to the third, and it would be negative. And x to the third is supposed to be negative. I'm good. All right. There's the regular sine function. What I'm supposed to do is I am supposed to find negative sine 2x over 3. And it's actually not that hard. What I'm supposed to do is negate the sine function, and then replace x with 2/3 x. So that's exactly what I'm going to do. I'm going to take each of these terms right here. Come on. My computer froze. I'm going to take each of these terms right here, negate them, and replace the x with a 2x over 3. So again, when you see me do this, when I have x to the 5th, it's going to be 2x over 3 to the 5th because the x is getting replaced with 2x over 3. And I was supposed to negate that, so that should be a minus over 5 factorial. And then minus becomes a plus, 2x over 3 to the 7th divided by 7 factorial. And since I have the original general term, all I'm supposed to do is negate it. So I'm going to take negative 1 to the n, and literally just throw a negative out in there. I could have also raised that to the n plus 1, because then it'll alternate starting in a different place. Doesn't really matter. And then x gets replaced with 2x over 3. Why, oh why, computer, do you do that? Nobody knows. Okay. All I did is take the base function and change it the way that it was changed in the expression. All right, let's try some other ones here. So what do I have next? I have negative x plus sine x. Okay, so let me change colors here. Negative x plus sine x. So for part D, if I think about this as an equation, what I've done is I've taken this side of the equation and I've added a negative x. So then I need to take this side of the equation and add a negative x, but I only add once. Addition does not distribute over addition. So all I'm really going to do is I'm going to take this right-hand side here and tack on an additional negative x. And hopefully some of you are screaming at me going, Mrs. Weber, can't you just? Yes, I can. Negative x cancels with the other x, and so it really becomes negative x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. But they told me they want the first 4 terms, so I just have to use my noggin and realize the next one would be x to the 9th over 9 factorial. And adding or subtracting does not change the general term. So even though this is technically a new series, I'm going to retain the original general term, because the general term is just what continues to propagate the series. It's not what starts it, it's what finishes the series. What's the pattern that continues it? I don't care what happened in the beginning. All right. And then we have cosine square root of 5x. Well, that one we're just going to take the cosine function and replace all the x's with the square root of 5x. So let's go through and do that. Let's see, how's my time going here? I just like to know. 12 minutes. Okay, so I want to pick up the pace here. So cosine square root of 5x, I will go as quickly as I can. So E is the cosine of the square root of 5x. So cosine is even, and so that's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then I have negative 1 to the n. I have x to the 2n over 2n factorial. And yes, that needs an exclamation point. Oh my goodness, Mrs. Vibber, you forgot the exclamation point in the other ones. Look at that. I got talking and I forgot. These need a factorial. My sincere apologies. Whoops. I get focused on what I'm doing and forget little details. Okay, there we go. Fixed. Over 2n factorial. So now if I want cosine square root of 5x, I am literally just going to change all of these into square root of 5x. Square root of 5x. Negative 1 to the n. Square root of 5x to the 2n. Over 2n factorial. Now, I can promise you that if this was like a question on a multiple choice, which you don't have multiple choice, but if it were, we definitely wouldn't leave it like this, because if you raise a radical up to an even, that radical is going to go away, and this is really hideous the way it is. So if I have the square root of 5x squared, it's just 5x over 2 factorial. The square root of 5x to the 4th is the same as 5x squared. And OneNote's doing that thing on me again, where everything disappears. There we go. 5x squared over 4 factorial. And then 5x to the 6th is like 5x squared. And then to the 3rd. So this would be 5x cubed over 6 factorial. So another way to write the general term would be negative 1 to the n, 5x to the n over 2n factorial. Okay, this is 15 minutes. I told you I was going to shorten them. So I'm going to stop here and then pick up with another video momentarily. So we've been talking about evens and odds, and I came up with a joke this morning. You know what's really odd? Y equals sine x. Even y equals cosine x says so. All right, you don't have to laugh. It's okay.